Okay, so this presentation is on Newton's laws of motion. You guys have done some labs on it, but now I just want to go through the three laws and just kind of talk about each one and just give you some, ideas and explanations maybe for your video that you're making. So the first thing I want to talk about is just force and what that means in physics class. A force is an action exerted on an object which may change the object's state of rest or motion. It is a vector quantity. So as you recall, a vector, of course, means it has a direction. Force is always in a direction. And a force is, the best way to think about it is just a push or a pull. Nothing fancy, anything that can push or pull an object. So if you push open a door, that is a force. The pull of gravity, that's a great example of a pull. Or if you pull on a rope, that would be a force. But a force does not have to cause an object to change its motion, but a force is a push or a pull. So if you're sitting in your chair, your motion is not changing even though gravitational force is working on you. So force is anything and any action that may change an object's state of rest or its motion. Okay, so Newton's first law, sometimes called the law of inertia. An object at rest will remain at rest, and an object in motion will remain in motion in a straight line at a constant speed unless it is compelled to change by an unbalanced force. So a lot of you knew that one. If you think about the tablecloth trick, you applied a force to the tablecloth. You did not apply force to the cup. So the tablecloth moves. The cup does not, because an object at rest remains at rest until you apply a force to it. An unbalanced force. Remember, a force may cause a change in motion. Okay, so if all the forces cancel out, as we'll start learning on Tuesday, the object will not move. But if the object has an unbalanced force, then it will move due to that unbalanced force. So now let's talk about inertia, a very important concept in physics. Inertia is a property of matter, as our good friend Bill Nye tells you. It's not energy, it's not mass. So it is just inherent in all pieces of matter. Now, how does this affect motion? Well, the more mass you have, the more inertia. More mass, more inertia. Number 3, inertia of an object does not depend on the object's motion. Inertia of an object is constant unless you change its mass. So only mass affects inertia. Only mass affects inertia. Okay, so the more mass, the more inertia. If mass goes up, inertia must be increasing. Okay? If velocity goes up, who cares? No effect on inertia. Okay, only mass affects how much inertia you have. If you look at number 4, okay, the law deals with motion in the absence of forces. Okay, so if there is no force acting on you, you will stay at rest or you will travel at a constant velocity. All right, so just to maybe help clear up inertia, let's think about this. If you have a bullet versus a bowling ball. Okay, so the bullet is fired. The bowling ball is rolling down the bowling lane. Which one has more inertia? Well, the bullet's moving faster, but velocity does not affect inertia. The bowling ball has the most inertia. Inertia only depends on mass. Okay. Inertia sometimes can be helped, think about it. How easy is it to change the motion of an object? How easy is it to change its motion? Well, a bullet has very little mass, so it is easy to change its motion. A bowling ball has a lot of mass, so it's harder to deflect it or harder to change its motion. Now, I know some of you are thinking, well, the bullet can go, right through you. That's true, but that's because of its aerodynamics and how it's made. Okay, so if there's any questions on inertia, please let me know. Newton's second law, sometimes called the law of acceleration. When a net external force is applied to an object, it causes the object to accelerate in the direction of the force. The acceleration is directly proportional to the force and is inversely proportional to the mass of the object. So if you look down here, if force goes up, acceleration goes up. Force goes down, acceleration must go down. Mass increases, acceleration will decrease, inversely proportional. If mass gets less, acceleration will increase. And you guys saw that in your graphs. Okay, you have force and acceleration. You got this line. And I believe if we had mass and acceleration, well, actually, I think we did acceleration versus mass, I believe. Okay, and you got this line. So direct, inverse, or indirect. So think back to that lab in your graphs, and that will help you remember what the second law says. So let's look at some points of the second law here. The law describes motion when a net external force is applied. Okay, so force is not equal to zero. Force is a number. So a net force does not cause motion, it causes motion or changes in motion. So it causes accelerations. Okay, so if force, is greater than zero, you will accelerate. Okay, that is a law of physics. If net force is greater than zero, you will accelerate. You're not going to travel at a constant velocity. You're going to accelerate. So what forces are acting on you? Well, you probably got gravity, probably friction of some kind. Who knows what else there may be. There may be a push or a pull. Okay. So why are you not accelerating? Well, your net force, if you added up all the forces, is zero. You are not accelerating because your net force is zero. As soon as net force is greater than zero, you will accelerate. So if you decide to stand up from your chair, you have accelerated for that short period of time. Okay. Now, two very important points right here. I'd love to see these mentioned in your videos. When force stops, inertia takes over. No acceleration. So when you release a bowling ball, and it's traveling down the lane, that is inertia. Okay, when I throw a baseball, as soon as it leaves my hand, that is inertia. So New Horizons is a space probe that NASA sent out there. It flew past Pluto. Okay, it doesn't have any rockets. Why does it keep going past Pluto? Inertia. As soon as a force stops, inertia takes over. You travel at a constant speed in a straight line. Now, what's the only thing that can stop a bowling ball, a baseball, or a space probe? That would have to be another force, right? That's what Newton's law says. Second point, if net force is 0, object is at rest or at a constant velocity. Okay? If net force is greater than 0, you will accelerate until that force stops. As soon as net force goes to 0 or the net force stops, you will travel at a constant velocity because of inertia. Now, the formula here is from the second law. So if you looked at the graphs and I had you find the slope, which I should have had you guys do, but I forgot about it. Force equals mass times acceleration. Mass is in kilograms. Acceleration is meters per second squared, of course. And for the metric system, force is measured in newtons. Okay, but F equals mass times acceleration. That's a very common representation of Newton's laws. Then I'm just putting arrows on top because that usually tells you that it's a vector quantity. We don't worry about that too much in CP physics, but I just wanted to make a note of it. If you see something with an arrow over it, that means it's a vector. Remember, it must have a direction. Okay, so the third law of interaction, when one body exerts a force on another, the second body exerts on the first a force that is equal in magnitude and opposite in direction. We paraphrase this: for every action force, there is an equal and opposite reaction force. All right, some points with the third law. The law deals with two different objects. So if I push on the wall pushes back on me. There are two different objects there, the wall and me. There are two different objects. Second point, forces always exist in pairs. You will never have a singular force. Okay. Key point here, number 3, there's an equality of forces, but not movement. I always like to say equal forces, not equal effect. Equal forces, not equal effects. Why did some people roll further on the skateboards in the hallway? Okay, there were equal forces, not equal effects. Okay, if every force has an equal and opposite, why don't they just cancel each other out? The forces are on different objects. Okay, when you push on the skateboards, person 1 was an object, person 2 was an object. Equal forces, not equal effects. Okay, why did the balloon move? The equal and opposite forces, right? The air rushed out of the balloon. The air simultaneously pushed on the balloon to move it forward. So the air was an object, the balloon was an object. Equal forces, not equal effects. Another point for Newton's third law is they always occur at the same time, right? The pair of forces, the reaction force, the action force always occur at the same time. So let's look at hammering a nail. The hammer exerts a force on the nail. Third law says the nail must exert an equal force back on the hammer. So if there are equal and opposite forces, how does the nail move? Well, remember, there's two different objects. You have the nail and the poorly drawn hammer here. Okay. So let's say I hit the nail with 100 newtons. Well, the hammer is going to be hit with 100 newtons, right? Well, 100 newtons on a nail will push it down. cause movement. 100 newtons on the hammer is irrelevant. The hammer doesn't notice. Okay, so 100 newtons on a little tiny nail will cause the nail to slam into the board. 100 newtons onto a heavy hammer does nothing. So equal forces, not equal effects. So let's think about the tug of war. How does anybody ever win a tug of war if there are equal and opposite forces? Okay. So here's my rope, my two people pulling on the tug of war. Okay, and again, let's say there's 100 newtons. Well, there has to be 100 newtons this way. So where does the difference come into play here? Because on a tug of war, on the rope, the forces do cancel each other out. So where is the other force coming from? So I'm pausing to let you guys think about that. All right, well, if you want to check with me what your guess is, that would be awesome. Okay, so hopefully this video will just give you some ideas, help clear up any misconceptions. We're going to talk about it in class on Monday a little bit. And hopefully, this will just start sinking in a little more. And instead of just memorizing the 3 laws, hopefully it will just become more of a understanding and not just memorizing, 3 statements. Another quick point I just want to make is make sure I understand that all 3 laws occur simultaneously. We learn them separately, but nature doesn't care about that. All 3 occur simultaneously. All right, talk to you guys later.